Okay, good afternoon, everyone. I'm a professor at San Jose State. I'm also one of the co-founders of Zero Chain. And today I'm here to talk to you about the work we've been doing specifically on our storage protocol as part of our ecosystem. So, the Zero Chain tagline is fast, free, flexible. So I want to talk about exactly what we mean by those different pieces. First up, what do we mean by fast? Well, we have very quick transactions and parallel bandwidth. And as far as our storage protocol is concerned, this is important for a couple of reasons. The quick transaction finality makes certain of our decisions make more sense. And also it means that we don't want to have our storage component overwhelm the mining transaction portion of it. Free, it's zero cost. Now, we'll talk a little more about exactly what we mean by that. But it essentially means that if you have zero chain tokens, you have access to use certain resources, but when everything is said and done, you don't lose those tokens. You can get them back and sell them or use them again or whatever you wish to do. And really the whole idea is to be a modular dApp framework. So our storage protocol is designed to try to be as modular as possible, so it stands as much separate from our mining protocol as possible, and it's just one component of our larger system. Okay, so to really look at the storage protocol, we have to consider who are the characters that are involved. So we're going to follow the standard security convention, and we'll have Alice. Alice is going to be our client. And she has a certain amount of zero chain tokens with which she wants to buy storage. And again, I have buys in quotes because she doesn't lose them, she'll get them back later. She can also apply erasure codes and encryption and the other things she needs to do to secure her data. The second person is Bob, and Bob's responsibility is to provide storage. So we call Bob a blobber, and he stakes a certain amount of tokens in exchange for promising to provide storage to Alice, and in exchange, he gets rewarded with newly minted zero chain tokens. Now, a critical thing about Bob is that he is not a miner. The miner is a different character in our protocol. So Bob provides storage, that's what the blobber's role, and the miner's job fundamentally is to verify transactions. So in the context of storage, there may be additional duties for the miner to make sure that Alice is connected with the right blobber for whatever her data requirements may need to be, to make sure that the blobber is paid for the work that he's doing, and if any disputes come up, make sure that he's able to resolve that problem. Now, of course, here we just have a single miner, but we all know that we have a network of miners, so whenever you see one miner on slides, picture a whole network of our 7 dwarves here. Okay. So the first step in this process is that Alice has to acquire the rights to some amount of resources. So she does this by locking her tokens. So what that means is for some period of time, say 3 months, she lends out her tokens, she loses access to them temporarily, and in exchange she gets a certain amount of access to resources, including both some amount of storage and then a certain amount of bandwidth, which we measure in terms of a number of reads and a number of writes. So in some sense, it's like she's loaning out her tokens to somebody else, and instead of getting interest, she gets access to certain resources instead. Okay, now once she's done that, she's ready to store her files, but the first thing that has to happen is she has to be connected with some blobber to store her data. So the way we do this is we initialize, she writes a transaction to the mining network. This includes her client ID that identifies herself, the ID that identifies the data she's trying to store, a timestamp to make sure that everything's fresh, optionally a Merkle root. And the Merkle root's the way of she can actually commit to the data that she wants to store. She doesn't have to do this. If she leaves this off, we assume that it's a read-only transaction. Then we have a bunch of parameters where she can specify things like what markets does she happen to want this data stored in. Maybe all of her customers are London, and she wants to make sure that the blobbers that are assigned to her are in that market. And then a signature to verify everything. Once the transaction is finalized, she gets back the identity of the blobber that she's going to work with, and now she knows about Bob. Okay, now a key thing about this is that we don't care about all the exact transaction details and exactly how the mining network works, as long as we have this API. As long as we're able to write a transaction with these fields and get back this information here. Now, once this connection is set up, we initialize the TLS connection, and the first thing Alice does is send across her transaction ID, which is a triple of this client ID, data ID, timestamp. And the point of this is this lets Bob actually look up on the blockchain to get back any data that's needed from that transaction, to verify that this is an authorized, allowed transaction, and also to get back the details about what the Merkle root is, so that he knows what content Alice is going to send him. Once we do that, we can begin an exchange of reads and writes between Alice and Bob. Now, the key thing here is that at this point, the mining network steps aside. So we don't have to overload the mining network anymore at this point. All the work is being done between Alice and Bob. Now, I want to talk a little bit more about these reads and the writes because the mining network is not involved, but we still want to make sure that Bob gets paid for the work that he's doing. So the way we do this is we create markers. Alice generates these, and it's sort of like she's writing checks to Bob for the work that Bob is doing for her. And here's the format of what we had for read marker. So we have a constant identifying that this is for a read action, the transaction ID. This means that Bob won't be able to spend the same marker again later. The blobber ID, so this is basically the to field of the check, so to speak, so that if somebody else manages to get these markers, they can't cash it in. We have a block number, which this is block in the data sense of the word, not the blockchain sense of the word. And lastly, we have this value I. Starts at 0 and Alice increments it, so that in case Alice is continually reading from the same block of data, Bob still gets paid for the work that he's doing. Similarly, we have a write marker, so that when Alice is uploading data, Bob gets paid as well. We have a different constant. The real big difference, though, is we actually include a hash of the data contents. And the interesting part about this is this gives Bob some proof that if he's storing data and there's some dispute later, he can show this to the mining network and say, no, Alice paid me to store this file, and here's my proof. Okay, so once we have these markers, we can have a bunch of exchanges happening, and eventually Alice says, okay, I'm done with this transaction, or maybe she times out, and Bob can then write another transaction to the network. This includes the ID of the original transaction plus the markers that he's received from Alice. And the mining network then verifies these transactions and deducts the reads and writes that Alice used, so it deducts the bandwidth she's consumed. It updates the Merkle root, and then most importantly from Bob's perspective, it ensures that Bob is paid in some newly minted zero-chain tokens. Okay, now this all works great as long as Alice is frequently reading the data or frequently updating the data, but what happens if Alice uploads some data and then just forgets about it and walks away? Well, we want to make sure that Bob is still paid in that case. So the way we deal with that is with a challenge request protocol, and this is a carrot and stick approach. If Bob can prove that he's storing the file, he gets rewarded with some new zero-chain tokens. If he doesn't, he gets punished and he loses some of the stake that he put up. So the first step is that the mining network will randomly post a challenge saying, basically provide me this block of data. And the blobber then responds back with that block of data plus the log-n Merkle tree nodes needed to reconstruct the Merkle root. So the neat thing about our protocol is we have this handshake between Alice and Bob where they agree on what the contents of the data should be based on this Merkle root. So we know that this challenge later, there shouldn't be any disputes. They've already agreed that this is what the data should be. And if Bob is able to provide what he should, he gets rewarded with some new tokens. If he isn't able to provide the data, he's instead punished. Okay. Now, we want to talk a little bit about the attacks and defenses, so we're going to do this a little bit backwards and start off with defenses. Of course, anytime you're giving something away for free, you have to be a little bit careful about that. So we have an economic protocol that's carefully tuning all the knobs to make sure that none of these attacks that we'll discuss will be profitable. We have an economics professor helping us to just get this tuned just right, and it is a complex part, but the idea is that none of the incentives will actually be in the attacker's interest to carry out. The mining network also is able to monitor all these transactions, although it's not directly involved in the file uploads. Nonetheless, there's enough information on the blockchain to be able to identify any odd or suspicious behavior, and then if a blobber is acting suspiciously, we can punish him and take away some of his stake. Also, we use erasure codes to give our data some resiliency. So if a meteorite takes out Bob's data center, or if Bob just gets mad and takes his machine off the network, we can still reconstruct Alice's data based on other fragments of the data that are out there. Now, a couple of attacks that come up in particular that we have to consider. One is outsourcing. What happens if Bob tries to, doesn't really want to store the data, so whenever somebody asks him for it, he gets it from somebody else? And because of our economic protocol and because of the way that erasure codes work, this attack isn't profitable because anytime anybody asks him to give access to a certain file, he has to pay 10 other people to provide the same data. So he has to pay 10 times to get paid once. The other attack that can come up is generation. What happens if Bob just makes up some file that he knows nobody's going to request, uploads it, and tries to get paid for that. Well, based on some of the challenge protocols we have and some of the way the economic protocol works, we're able to defend against these. Okay, so future work and where we're going from here. So one of the pieces is that at the moment we can reconstruct data if Bob happens to disappear or we lose a chunk of the data that's out there. However, this requires that the client is involved in the process and gets the information to reconstruct it. We're working on making it so that the mining network can actually reconstruct the data without ever involving the client. So they realize the blobber's not doing their job and the miners can actually reconstruct and reassign the data to somebody else so that the client never notices that anything's wrong. We also, currently, the way our protocol works, it works really well if we're doing read-only transactions or write-only transactions, but what if we want to have an interactive session between Alice and Bob? So the markers that we have that basically commit Alice to the data she's uploading can be used as part of this process. So we're looking at how the blobber can actually verify the data that's out there without requiring the client to commit up front. Okay, just the final plug for Zero Chain. We've gone through how we can provide free storage with our modular design that most importantly doesn't overload our mining network with too much data, with too many transactions. Thank you very much for your time.